So we talked a lot about covalent bonds before we got into Lewis structures, and then how to represent covalent bonds by Lewis structures. So now I'll say a little bit about ionic bonds, which are the other extreme. And when you have an ionic bond, what you have now is a complete transfer of either one or many electrons between two atoms. So the key word for covalent bond was electron sharing. The key word for ionic bonds is electron transfer. And the bonding between the two atoms ends up resulting from an attraction that we're very familiar with, which is the Coulomb, or the electrostatic attraction between the negatively charged and the positively charged ions. So let's take an example. The easiest one to think about is where we have a -1 and a +1 ion. So this is salt, NaCl. Actually, lots of things are called salt, but this is what we think of as table salt. So let's think about what we have to do if we want to form sodium chloride from the neutral sodium and chlorine atoms. So the first thing that we're going to need to do is we need to convert sodium into sodium plus. What does this process look like to you? Is this one of those periodic trends, perhaps? Can anyone name what we're looking at here? Exactly, ionization energy. So if we're going to talk about the energy difference here, what we're going to be talking about is the ionization energy, or the energy it takes to rip off an electron from sodium in order to form the sodium plus ion. So we can just put right here, that's 494 kilojoules per mole. The next thing that we want to look at is chlorine. So in terms of chlorine, we need to go to chlorine minus. So we actually need to add an electron. This is actually the reverse of one of the periodic trends we talked about. Which trend is that this is the reverse of? Electron affinity, right? Because if we go backwards, we're saying, how badly does chlorine want to grab an electron? Chlorine wants to do this very badly, and it turns out the electron affinity for chlorine is huge. It's 349 kilojoules per mole. But remember, we're going in reverse, so we need to talk about it as negative 349 kilojoules per mole. So if we talk about the sum of what's happening here, what we need to do is think about going from the neutrals to the ions. So we can just add those two energies together. And what we end up with is plus 145 kilojoules per mole in order to go from neutral sodium and chlorine to the ions. So the problem here is that we have to actually put energy into our system. So this doesn't seem favorable, right? What's favorable is when we actually get energy out and our energy gets lower. But what we're saying here is that we actually need to put in energy. So another way to say this is this process actually requires energy. It does not emit energy. It does not give off excess energy. It requires energy. So we need to think about how can we solve this problem in terms of thinking about ionic bonds. And the answer is Coulomb attraction. So there's one more force that we need to talk about, and that is when we talk about the attraction between the negatively and the positively charged ions, such that we form sodium chloride. So this process here has a delta energy, a change in energy of negative 589 kilojoules per mole. So that's huge. We're giving off a lot of energy by this attraction. So if we add up the net energy for all of this process, all we need to do is add negative 589 to plus 145. So what we end up getting is the net energy change is going to be negative 444 kilojoules per mole. So you can see that, in fact, it is very favorable for neutral sodium and neutral chloride to form sodium chloride in an ionic bond. And the net increase, then, it's a decrease in energy. So I just gave you the number in terms of what the Coulomb potential would be in attraction, but we can easily calculate it as well using this equation here, where the energy is equal to the charge on each of the ions, and this is just multiplied by the value of charge for an electron, divided by 4 pi epsilon naught times r, and r is just the distance in terms of the bond length we could talk about. So let's calculate and make sure that I didn't tell you a false number here. Let's say we do the calculation with the bond length that we've looked up, which is 2.36 angstroms for the bond length between sodium and chloride. So we should be able to figure out the Coulombic attraction, if I can find my good chalk here, for this. So if we talk about the energy of attraction, we need to multiply plus 1, that's the charge on the sodium, times minus 1, the charge on the chlorine, times the charge on an electron, 1.602 times 10 to the negative 19 coulombs. And that's all divided by 4 pi. And then I've written out epsilon naught in your notes, so I won't write it on the board. And then R. So R is going to be 2.36 and times, what is angstrom, everyone? Yep, 10 to the negative 10th. So 10 to the negative 10 meters. So if we do this calculation here, what we end up with is negative 9.774 times 10 to the negative 19 joules. So that's what we have in terms of our energy. That does not look the same as what we saw. Oh, yep, do you have a question? Oh, square this value here. OK. Luckily, although I did not write it in my own notes, I did it when I put it in my calculator. Thank you. So you need to square this value here, and then you should get this value right here, negative 9.77. All right, so what we need to do, though, is convert from joules into kilojoules per mole, because that's what we were using. So if we multiply that number there by kilojoules per mole, or excuse me, first kilojoules per joule, so we have 1,000 joules in every kilojoule. And then we multiply that by Avogadro's number, 6.022 times 10 to the 23 per mole. What we end up with is negative 589 kilojoules per mole. So this is that same coulombic attraction that we saw in the first place. So notice that you will naturally get out a negative charge here. Remember, negative means an attractive force in this case, because you have the plus and the minus 1 in here. So we should be able to easily do that calculation. And what we end up getting matches up with what I just told you, luckily. And thank you for catching the squared. That's an important part in getting the right answer. So experimentally, then, what we find is that the change in energy for this reaction is negative 444 kilojoules per mole.